Hi everybody, this is Mrs. Valdivia, and today we're going to be talking about Chapter 1, Foundations of Chemistry. Don't mind my dog in the back, she fell asleep and is snoring a lot. Okay, so in Chapter 1, on the Rebel Introductory Chemistry textbook, we're going to start off by talking how chemistry is in everything we do. Every single little part that we look at, our history, the physics, engineering, healthcare, every field, chemistry is involved in it. And that is because chemistry interfaces with all of these other fields. They all have science in them. So no matter where your passion lies, whether it's art, music, math, sports, right? You want to hit the weights or the gym, but you want to know the chemistry behind how to make bigger muscles or how to run faster. There's chemistry behind it. And we could see that through all these different fields. Well, there's a couple vocabulary words that we need to describe. Chemistry is the study of matter and its changes. Matter is defined as anything that has mass and takes a volume. For example, in this image, we see the clouds, we see air, and you see water. And far away, you see a little sailboat. All of these are composed of matter. As we explore chemistry, we'll explore what these different forms of matter are made out of and how unique substances behave. So let's look at the difference between composition of matter and the structure of matter. Composition refers to what something is made of. Structure is a broader term. Okay, what something is made of and how are the components arranged? We want to know those different things. So consider these three objects that we have. We have a deck, a canoe, and a baseball bat. All of them have the same composition, right? What's that composition? They're all made out of wood, but the structure is different. The arrangement of the wood allows for us to use them differently. For example, the canoe can float in water. Now let's identify pure substances and in elements and in compounds. So an atom is the fundamental unit of matter. Okay, one more time. An atom is the fundamental unit of matter. They're tiny, tiny little spheres. Okay, well, at least that's how we're going to describe them for the purpose of this class, this presentation, because we know we could break an atom apart. Okay? And we're going to discuss the details of an atom further on. An element is made of only one type of atom. Okay, so an element is made of only one type of atom. So, for an example, this sphere represents one atom. Cl represents chlorine. Chlorine is an element. Another thing that represents an element, for example, is this gold bar. Gold is made out of one element only. Tons of atoms, as you can see from this picture, tons of atoms squeezed together to make this gold bar. And it's pure gold. So it's a pure substance. Nothing else is inside of this. Now let's look at compounds. Compounds are substances that are composed of more than one element. So they have fixed ratios. Let's look at water. Water is a compound with a fixed ratio. It's made out of two hydrogens and one oxygen atom. Many compounds form different groups and they're called molecules. In molecules, the atoms bind tightly together and they behave as a single unit. So water is a molecule, by the way. Some elements also exist in diatomic molecules. So example here, we have hydrogen. It could also be nitrogen, but diatomic means that they come in twos, right? And if you guys look at a periodic table, so here's our lovely periodic table in our book. It's in the actual front cover of it. There are certain elements that exist in diatomic form. So let's go over those really quickly. Nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, as well as hydrogen. So they form a lovely little 7 on your periodic table. Okay. One more time, those are diatomic, which means they exist in a pair of two, when they are in their pure elemental form. All right, so let's look at this element right here. What do we think this element might be? We can recognize it right away by its physical characteristics. This element is copper, right? Copper has a huge contrast to all the other metals. It's color that can only be described as the color of copper. So water is a molecule and copper is an element. In this case, water is flowing out of copper. And the beautiful thing about this is that these two items that we have, they're both pure substances. Copper is a pure substance in elemental form, and water is a pure substance in this molecule form with a fixed ratio. All right, now that we've talked about pure substances, let's go into mixtures. Mixtures contain more than one substance. They're not bound by fixed ratios. So the statue that we're going to see right now, this one right here, is a mixture of metals. So this metal is called bronze, and it's a mixture of copper and tin. It has different properties. The mixture allows it to have different hardness, different colors, and these are called alloys, metal alloys. Right. Now we have two different types of mixtures. We have a homogeneous mixture and we have a heterogeneous mixture. So homogeneous mixture means components are mixed evenly throughout. A heterogeneous mixture means they're not mixed evenly throughout. So homo means even or same, hetero means different. So if we look at the examples, this homogeneous mixture is a mixture of salt that has evenly mixed with water. And this one's a heterogeneous mixture of sand and water. You could see that the sand is separated from the water. Let's look at other mixtures that we might see in everyday. Look familiar? Cookie dough. All right. So cookie dough is one of those mixtures that we're going to consider a heterogeneous mixture. We could easily pick those chocolate pieces out of the cookie dough and separate it, the chocolate from the dough. Okay. The other picture that we have here is a mixture of a substance going into a liquid. And as you can see, when we're mixing these two clear liquids together, they're producing something cloudy and white. This is called a precipitate. So it is producing a precipitate. It's not mixing in together nice and finely. This is also a heterogeneous mixture. Here's a molecular view of it, and you can see that you have your water, and you have water separating your compounds or little compounds inside of your water. Another one could be our coffee. Okay, so coffee, can we separate it? Can you separate the caffeine from the water? No, it's already been filtered, right? So it's already been filtered, and in this case, this is considered a homogeneous mixture. We cannot separate it. Another mixture that we don't think about that is homogeneous is the air that we breathe, all right? So the air that we breathe is a homogeneous mixture. Right? Every time we take a breath, we don't separate the nitrogen from the oxygen. We just breathe it in. We have nitrogen, oxygen, carbon dioxide, or some carbon monoxide, whatever other toxins might be in the air. But we breathe those in evenly. So it is a homogeneous mixture. Right? Okay, how do we separate mixtures? So in the lab, there's different methods that get used to separate mixtures. One of the basic forms of separation is a filtration separation. So when you filter something, you could separate heterogeneous mixtures, right? You could pour, in this case, you have sand and water mixed together. And if you have a filter, it could trap all the sand and just filter out the water. And you're just going to get some nice water at the bottom. All right, now this following chart, I actually recommend that you guys copy this chart down, right? As we write it out, okay? This is a very useful chart in helping you identify pure substances and mixtures and what they lead into. So we can divide matter into pure substances and mixtures. Elements are substances made out of only one kind of atom. Oops, wrong way. And we talked about gold being one of those elemental forms. Copper is also one of those elemental forms. Then we have compounds, different types of atoms bound together. We used water as an example of a pure substance that is a compound. Now let's look into mixtures, homogeneous mixtures and heterogeneous mixtures. Homogeneous means your compounds are evenly blended together, like the air that we breathe. A heterogeneous mixtures, they're not blended together. So example, this precipitate that has formed inside of the water. We have three states of matter. Well, there's four, but we're going to be discussing the three states of matter here. We have solids, we have liquids, and gases. Solid, liquid, and gas. Three states of matter. A solid has a definite shape and a definite volume. A liquid has a definite volume, but no definite shape. And gas, no definite shape or volume. What does this even mean? Okay, so example, I could take that gold bar, right? I could just pick it up and I could put it on a plate and it's gonna have the same shape. I could take that gold bar and put it in my bathtub and it's still gonna have the same shape. The shape is not gonna change. Now, I could take this soda, right? And I could pour it in a plate and it's gonna just spill out. I'm gonna have the same amount of soda, but it's gonna have a different shape. I could take that soda and I could put it in a balloon. So if you put water in a balloon, it doesn't always maintain its shape, right? You could squish that balloon and that water takes up the shape of whatever you're doing to it. So it has no definite shape. Um, Using open containers though, like just switching it from open containers, if you take a can of soda and you put it inside a 1 liter jar, you don't automatically get 1 liter of soda. You still have one can with your 8 ounces of soda. So your quantity doesn't change. Your volume is definite, but your shape does change. Okay, to conform to the figure that it is in. Now let's look into gas. Gas has no definite shape and no definite volume. Gases fill any container they occupy. They will fill any container that it occupies. No definite shape, no definite volume, and they're constantly moving. So they're molecules that are in constant motion. Okay, so how are properties affected by temperature? Well, let's look at a solid that doesn't really move, right? At room temperature, everything is pretty much a solid here. That's how we look at things. We compare it to our room temperature, right? Liquids are solids melt to turn into liquids, right? And a liquid evaporates to turn into a gas. Now, if you notice, solids have this slight little motion right here. It means it's slightly vibrating. So everything has a constant motion. A solid, even though it looks steady and still slightly vibrates. Okay, unless it's absolute zero, in which everything stops moving, which we don't have here, thank goodness. You're going to have some slight vibrations and movements to your atoms. So if we start cooling something down, when we cool something down, we're obviously going to get the opposite of what's happening here, right? Gas turns into a liquid through condensation. A liquid turns into a solid through freezing. So the opposite reactions happen. We could also have them skip. A solid could go into a gas right away, sublimation. So like carbon dioxide or dry ice. If you take dry ice and you leave it on the table, you're not going to see a puddle of water. There's no puddle of CO2. It's going to evaporate instantly. The states of matter offer important lessons to us. They determine the type of behavior that a substance is going to have. So, behavior of any substance is determined by what it's composed of, the arrangement of how it is composed. So, if you look at the pictures that we have here, you have a solid gold and then you have melted gold. What's happening at its atomic level? Can you guys see it? Do you see the differences between the molecules, between the solid and the melted or liquid form of it? Yeah, I do, right? You see this one, it's nicely organized, packed together. It looks kind of neat, right? Someone came and did a lot of hard work there. And this one, the atoms are just jumbled up everywhere, right? They are like moving around, okay? There's some energy in here. They are in motion. So we know physical properties is another thing we describe all our elements with. What is a physical property? So a physical property can be measured without changing the identity of the substance. So you can take the mass of copper, right? And you're like, okay, that's something that we can take, right? It's a measured quantity. You could also take the volume of copper, the temperature, the color, the hardness of it. How hard is this copper? And still, you're not going to change the identity of that copper. So the copper pipes that we have here, you can weigh it. So when I say you take the mass, that means you're weighing it. How much does it weigh? The volume, how much do you have? How much space does it occupy? The temperature, is it colder or hotter, right? But in this case, it's measured temperature. So we're going to be looking at it in degrees Fahrenheit or degrees Celsius, um, mainly degrees Celsius. The color, can we describe it? Yeah. And it's not going to change, right? So physical changes don't change the identity of a substance. Can I take this copper wire and flatten it out? Yes, I can, and it's still copper. Can I take this copper wire and turn it into something else? Yes, I can. and it's still copper. And in this case, copper is a solid, right? It's a solid in both this wire form or pipe form and in this spigot form. So when we look at physical changes, when we do have any kind of physical change, physical changes are phase changes. So what does it mean to have a phase change? A phase change means that you're going to go from solid to liquid, liquid to solid, liquid to gas, any kind of formation, just when you're switching between them. Are you getting melted, frozen, evaporated, condensed? All of those are phase changes. You're altering the shape of your substance. Okay, you're altering it. You're going to either mold it, you're going to cool it, whatever it is that you need to do, but it gets altered. Now let's look at properties that do change. Okay, chemical properties. So chemical properties are properties that we cannot measure without changing the identity of a substance. So for example, flammability is a chemical property. If we want to determine if something is flammable, we must try to burn it. If it burns, it is no longer the original substance. When a substance changes into something different, it has undergone a chemical change. Chemical changes are also called chemical reactions. So let's look at this burning of our wood right here, right? It started off as wood, and then we had a combustion reaction. So a combustion reaction means that we had some sort of heat react with our oxygen and it ignited. We needed an ignition source. This is no longer wood anymore. It's changed its composition from carbon to carbon dioxide. You cannot get that wood back. Chemical reactions allow us to combine elements together. And when we combine elements together, we can create different compounds. So let's look at this example of zinc and sulfur combining together. When they combine together, we make zinc sulfide. The compound has properties that are different from those of the elements that compose it. Let's look at another one. The change that forms new compounds, a chemical change. Okay. So in this case, we have butane plus oxygen. So butane plus oxygen. We give it a little ignition source, and boom, we're producing carbon dioxide and water. So your key idea is that a chemical change always involves the formation of different substances. All right, properties and changes. So chemical and physical changes. Chemical changes, remember, change the identity of a substance. Chemical properties cannot be measured without changing the identity of a substance. By contrast, measuring physical properties in all its changes, we do not change the substance. It doesn't change. So you can measure physical and not change it, not hurt the substance. However, if you're going to change the chemical, well, you're actually changing your substance. Hmm. Another topic here, energy. All right. So energy is basically everywhere. It's the ability to do work. Okay. So one more time, energy is the ability to do work. It takes up two forms, kinetic energy and potential energy. Potential energy refers to stored energy. That means energy that is waiting, right? It's waiting to turn into kinetic energy. It has it in it. Okay? Kinetic energy is energy in motion. So the faster an object is moving, the greater the amount of kinetic energy it has. Oh, and these rocks right here is just to represent, you see how nicely balanced they are? This is potential energy. potential energy. Because if this were to tip over, the moment it starts tipping over, it's going to turn into kinetic energy. And by its weight, it's going to hit really hard and it's going to have a lot of kinetic energy. It's going to fall fast. Don't be underneath that if it falls. Heat energy. Okay? So heat energy is a type of kinetic energy. It involves particles within a substance. So when a substance is heated, the particles within it start vibrating. They move and move and move more quickly. The more you heat it, the faster they're going to move. So here we have a stove. The particles on the hot surface vibrate more rapidly than when the stove is cold. We could touch a cold stove, and that's because the particles are not vibrating. On a microscopic level, the stove doesn't have kinetic energy. It's sitting still. But in an atomic level, the particles on the surface of the stove are moving super quick. So remember, macroscopic level is the big picture, macro, big, right? We see a stove, we don't see it moving, we don't see it vibrate. But in the atomic level, it's moving. This part right here, it's heated, it's hot. Vibrations everywhere. All right, physical and chemical changes involve changes in energy. So if you're moving from higher energy to lower energy or moving from lower energy to higher energy, okay, you're releasing energy. So as you're rolling down the hill, you're releasing a lot of that energy, right? Um, so changes that release energy are called spontaneous changes. And when you're pushing a bike up the hill, okay, that's different. You're inputting energy. So you're no longer releasing energy. It takes energy to do that. So this one here, releasing energy, right? This one here, you're inputting energy. You're working hard to push that bike up the hill. So you're creating work. Right? So energy changes take many different forms. And one of the chemical reactions that I mentioned earlier was a combustion reaction. So if you look at a tree burning, a tree has a lot of stored energy, tons of stored energy. And when you ignite a tree, it burns and you feel the heat, right? We use firewood for camping and whatnot because it produces heat. Wood has a lot of stored heat. Now, obviously, we don't like to see a forest burn, but that's the reason they burn so fast. Trees have a lot of energy inside of them. And every time we have a combustion reaction, we release carbon dioxide and water. All right, so looking back at this rock, we want to know, is this stable? Is this not stable? Okay, apologize. So the stability brings about some sort of change. In this case, we're not going to be changing it chemically. It'll only be changing physically. Okay. So these rocks right here, you know that time and erosion, right, has left them the way they are, and they're very, very nicely balanced. Because the rocks are sitting high off the ground, they have tons of potential energy. Okay, tons of potential energy. However, once they fall, remember that's going to turn into kinetic energy. All right, so let's look at this trap, mouse trap right here, see if we can kind of figure this out, this little trigger. So this part here has tons of potential energy. And the moment you trigger and set it off, boom, you no longer have that potential energy. You've released it as the form of kinetic energy. Here's another one. Okay, in this case, we have a simplified structure of ethylene oxide, and it behaves just like a mousetrap. It's holding tons of potential energy inside of it. And when you combine this ethylene oxide with water, you create a new water molecule. Sorry, you create a new compound. Oops, lost my page right there. This new compound is more stable, okay, and it has lost its potential energy. All right, so let's talk about what kind of changes energy is. So the release or the gain of energy. Releasing energy is called exothermic reactions. So when you burn something, when you feel heat, you have exothermic. So exo, to exit. If you guys remember that, exo means exit, right? To leave. So you're exiting the system, right? Heat is exiting, exothermic, feels hot, right? Now in this case right here, you're adding heat to the water. Okay? When you're adding heat to it in order to boil it from the bottom up, that is an endothermic reaction. So you have to add heat in order to convert water to steam. Endothermic. Endo, to enter, enter inside, right? Come inside, enter inside, right? Energy is there. All right, scientific method, not going to go over it too much right here, but we kind of already know the scientific method. We studied this over elementary and middle school and high school, right? So with scientific method, you always want to make observations, formulate ideas, test those ideas, right? Create a hypothesis, a theory, what's happening. So an explanation and ideas that support your evidence or your explanation. And your theories might not always be right. And if that's the case, make more observations, formulate new ideas and theories, and test them out. So the difference between theories and laws. Theories, how or why it happens. Law, what has happened. Okay. Um, Theories and laws are a little bit different. Okay. So scientific laws provide a concise description of behavior. So they tell us what is happening. On the other hand, theories explain how or why something is happening. All right, you guys. So this covers chapter 1's foundation of chemistry. And hopefully you guys took some little notes on there. This could probably all be summarized into, let's say, 5 pages, big handwriting, notes, single-sided. I'll see you guys next time for the next chapter. Ciao.